So last time we saw how to get a representation on the tensor product of two representation, and that allowed us to give representation on tensor powers, and the same technique sort of you can use to give representation on exterior powers and symmetric powers. Yeah. So I'll talk about dual representation today, and then we will go on to talk about characters of a representation. So that's an important concept. It's an invariant of a representation, but it more or less determines the representation. So let's talk about the dual representation. Yeah. So if V is a G representation, we can form this dual vector space. So these are all K linear maps from V to K. So we want to say, so we want to give a linear action on V dual. Yeah. So if I give you phi, we want to know what is net phi belongs to V star. We want to know what should be G phi. Yeah. Same font. Yeah. So what is G phi? G phi is going to be another element in here. So so what should it be? Yeah. So so it should be a linear function. So we want to know G phi of V. What should it be? Yeah. So of course, one thing one can guess is that G phi of V, or maybe you can try it as phi of GV. Yeah, but that may not work. Yeah, so there may be some problems. So I'll tell you some things we also want from this representation. So I can give you the formula, but maybe I'll try to motivate it. So there are two ways to think about it. So first of all, we know that if we have V star, then of course there is a pairing between V star and V. Yeah. What is the pairing? So sorry, maybe pairing, I can write it as a map. Yeah. So there is a pairing from V star cross V to the base field K. And what is the pairing? So if you have a linear map from V to K and you have an element in V, the only thing you can do is just evaluate it. Yeah. So that is the pairing. So so one way to think about it is we want this so the representation should somehow behave well with respect to pairing. So we want G phi. So whatever this definition is, we would like that this to happen. Yeah, should be same. This pairing should be, so after the action, the pairing is preserved. Yeah, so this should be same as phi. So that means it is this pairing, it behaves well with respect to pairing. So this is one way of thinking about, and then we will have to check what is the right definition. Yeah. So G phi evaluated at GV should be same as phi evaluated at V. Yeah, that is what we are trying to say. Okay. So G phi evaluated at G dot V should, instead of G phi evaluated, should be same as phi evaluated at V. So this of course is different from G phi evaluated at V is phi of GV. Yeah. So even regular representation, when we were trying to do, I wrote regular representation. So the group ring, I wrote it as linear combinations of elements of G. Yeah, K linear combinations of elements of G. But group ring, I can also think of it as functions from G to K. Yeah. So if you take the functions interpretation, then the action will be somewhat different. Yeah, it won't be this. So maybe there is an exercise which I'll give, and that you can verify that if you use the function thing, then the action is going to be this thing. Yeah, G phi V is phi G inverse V. So this is true. So we will see that this is the right way to think about. So this is the action. Okay. So G phi of V should, I mean, if you want this condition, this implies this. Yeah. So if you want this property, then G phi of V should be G inverse of phi of G inverse V. Yeah. So this is consistent with this. So we will see that this is indeed an action. So this is a linear map on G on V dual. That is not difficult to check, but that means G. So that is just to check that G dot phi is linear. Yeah, that is okay, because G is a linear map and phi, of course, is linear map. So, but it's also an action. So we'll check that it's an action. Another way to think about it is you have maps from V to K, yeah, and of course there is a action of V on there is an action of G on V, yeah. So you are given a phi, and you are given a G phi, yeah. So G so when you act on G, you will get G phi, yeah, and of course that will map to K. So V to V, this so there is a map using G, yeah. So this group for each group element, you will get a map from G to G, which is rho G, yeah. So and you consider the since there is no action on K given, so K you think of K as a trivial representation, yeah. So there is G acts trivially on K. So you want this diagram to commute, yeah. So you go this way or you go this way, so it shouldn't matter. So what does this diagram to commute means is that if you take V in V, then you first apply. So this condition will be same as this condition here. Yeah. So so you will see. So maybe I'll just write it down again. Okay. So for instance, you take V in V, you apply G, and then apply G phi. That should be same as you first apply phi, and then there is no action. Yeah. So this is phi. So this is another way of saying that it should preserve pairing. So this diagram should commute. So I'm just trying to motivate why this definition is the right one. So in general, we will define home VW when V and W are two representations. Yeah. So so then the action should be in these terms. Yeah. So more generally, if VW are two G representations, then we want to then home VW also has a G representation. Yeah, and then so it has a natural G representation, and then so the guy we'll have is G dot fish evaluated at V should be sorry, evaluated at GV. So let's write it this way. So then the relation will be, so here you just put, instead of K, you put W there. Yeah. So this diagram should commute. Right? So first you apply G, then G evaluate it, evaluate it at via G phi, and that should be same as first applying phi to V, And then now W, the representation is not trivial. Yeah. So whatever element you get in W, you apply G to there. Yeah. So this is how this map is defined. G phi is defined. Yeah. So if you want to write it without this inverse, without this, you want to write it as a function instead of putting here. So you'll want that G phi V should be G dot phi G inverse V. Yeah. Right. So this will be the this will be, so one has to check that this is again an action, G dot phi, and G phi is an action. So that is similar to showing that this is an action. So I'll show that this is an action, and that you can check yourself. Okay. So now that I hope you are convinced that this is the right definition, let's just check that this is indeed an action. Yeah. And that will prove that V dual is a representation. And similarly, this is also a representation. So what do we have to show that this, what do we have to do to show that this is a representation? We take H, so of course, if you put identity, that check is trivial. Yeah, E dot phi is phi itself. So the only thing we have to check is that Hg times phi is same as Hg dot phi is same as H dot G dot phi. Yeah. So let's see what is Hg dot phi evaluated at phi. Evaluated at V is just phi of Hg inverse V. Yeah. Which is basically phi of G inverse H inverse V. Yeah. So which is same as now. So phi of G inverse H inverse V is just G by this definition, which we have done here by this definition. This is same as saying G phi is and this is G phi of H inverse V. Yeah, that if you apply that formula. Okay. So yeah.
Sir, over here, the G dot phi in the right hand side, is it like the action of G in the space W? That's a different action.
Yeah, talking about
the map G phi, right?
Yeah. So yeah. So maybe I should have written it in terms of yeah. So this G dot phi G inverse V. This G dot this is the yeah. So you're right. So this looks a bit confusing. Yeah. So maybe I should put brackets at the right places. Yeah. Is this better?
Oh, yes. Sir. Like this is the function and this is the action.
Yeah, exactly.
Okay.
And this is, yeah. So maybe, okay, maybe this formula, I'll write it in terms of rho. Yeah. So that there is less confusion. So this is the action in W, and this is the action in home. Yeah, so then it will become even more complicated to write. So okay, but anyway, I'll write the form. I'll rewrite this formula. Yeah. So let me do that. So rho home. So I'll just abbreviate and the representation for rho. Yeah. So rho home of G. Let's just get rid of the subscript here. Yeah, this evaluated at, so this rho home of G is going to be a representation of, yeah, so it's a representation of home VW, yeah. So if I take a phi here, it will give me element, yeah. So rho home of G is an invertible element of home VW, yeah. And if I take an element of home VW, it will act on it and it will give me another element of home VW, yeah. So so this element of home VW, how does it act on V is what I'm trying to say, yeah. So what I have so far written is the left hand side. So this, if you try to write in terms of rho, it looks this complicated. Yeah, so there is a reason one uses this kind of notation. This should be same as rho W of G evaluated at Rho W of G is a action on is now a linear map from W to itself. Yeah. So that is same as phi of. So image of phi is in W. Yeah. Phi of rho rho V of G inverse. Rho V of G inverse is a linear map on V. So you can evaluate it at V and you get something in V. Then if you apply phi to it, you get into W. Yeah. Okay. So it I don't know if I made things more complicated or more simple. But this is accurate. Yeah, there is no. I mean, the advantage of this complicated expression is that there is no problem with the I mean, there is no possible of misinterpretation. Okay, but of course, you think of it like this. I mean, meaning you think so. You think of it like this, but you write it this way. Otherwise, people will get more confused. Yeah. So. But there should be clarity where this dot is. Yeah. So as I said, we should be very careful about the notation. Last time also there was some confusion about the notation. So all these dots are different. This dot, so for instance, this dot is the action on G action on home. This dot is the G action on W. And this, where I haven't even put a dot, maybe, yeah, G dot B. This dot is this dot is the action of G on B. So there are 3 dots defining different actions, yeah? And I'm using the same dot for it. But from context, hopefully it is clear. But without the bracket, even that is not very clear, yeah? So maybe bracket here. Okay, so hopefully now things are better. And phi v is anyway, yeah, so bracket here. Phi v is element of W and you are acting on it. Okay. I hope this is clear now. Yeah, any questions?
So it's clear, thank you.
Yeah, okay, great. Yeah, thanks for that question. I think it has become much more clear now. Okay, so now you think about why this is an action. So in the spirit of putting more brackets, let's just put a bracket here. Hg times phi is going to be an element of home. Is going to be an element of V dual, yeah, and we want to show that Hg, the action of Hg on V is same as action of G on V followed by an action of H on V, yeah. So we sort of evaluate it. So this is phi of, by this formula, this is phi of Hg inverse of V, where G inverse is same as G inverse H inverse. And of course, this is the action on V, and of course, this is indeed an action. So this you can think of it as H inverse V followed by G inverse V. Yeah. Now, you use this formula and with V replaced by H inverse V, and you get that this is same as G phi of evaluated at H inverse V. And again, this you replace phi by G phi and G by H, and then you see that this is H dot G dot phi evaluated at V. Yeah. So this is same. So that tells you that Hg dot phi is same as G dot phi. First you apply G to phi and then apply H to phi. Yeah. Is this okay? So this hence it is an action. So this formula determines an action of G on V dual. Okay. Any questions so far? Okay. So this looks somewhat complicated, but or whatever, maybe not too complicated, but we also want to write it in terms of matrices. Yeah, so in terms of matrices, it should become somewhat more transparent. But here, of course, if you want to write, rho G is is a matrix, but you have, for that you have to fix a basis of V. Yeah, and then rho V. So you have rho V star G will also be a matrix, but for that also you will have to fix a basis of V star. So of course, if you fix some random basis of V and some random basis of V star, then you don't expect any relation. Yeah. But if you fix some dual basis, then there will be a relation. Yeah? So let E1 to En be a basis of V, and then you take the dual basis of V star. Yeah? So E1 star to En star. So dual basis precisely means that Ei star Ej should be delta Ij for all Ij. Yeah? So I hope you know what dual basis is and dual vector spaces are. Yeah? Are you familiar with this? Did you see that in linear algebra? Hello, are you guys there?
Yes, sir.
Yeah. So did you see dual vector space and dual basis, etc. in linear algebra?
Yes, sir. Most probably, like not in very deep details, but the basic things we did, like that one at EI and 0 at other places.
So this basis, you know that, for instance, these dual vectors do form a basis, for instance, yeah?
Yes, we have seen that.
Okay, so that is all we need. We don't need too many details, yeah? So this is indeed a basis. Now we want to figure out, so I want to get a, so if I have given, I'm given, so suppose rho Vg is a matrix with respect to E1 to En, yeah? So I want to know what is rho V star G in terms of matrices, but now with respect to this basis, dual basis, yeah? So then that way, so you eventually, if I give you a representation of V, you would like to compute the representation of V dual. Yeah, it shouldn't be some abstract thing. So maybe what is the matrix with respect to dual basis is a good way to think about it. Yeah? So let's try to unravel the definition and see what you get. Yeah. So let phi be in V star. We want to know, so we want to determine the matrix of this with respect to E1 to En, E1 star to En star. Yeah? So let's first understand what is happening. Yeah. So suppose phi is in V star, some arbitrary functional. Yeah. So you can write it since E1 star to En star is a basis, you can write it as write down the coordinates of phi in terms of E1 star to En star. So what that is, you'll get, this will be U1 to UN with respect to this. So what this means is phi is summation UI EI star. Yeah. So UIs are, so here UIs are in the base field. Yeah, so you get a column vector. So this is, so this of course you must have seen in linear algebra. Whenever you have a basis, you can write it this way. So I'm trying to write the coordinates of phi in terms of this dual basis. Yeah. So I need to know where does G phi go. Yeah. So if I know where does G phi go, then maybe I can write it in terms of some matrices. Yeah. So actually, I only need to know about the E1 star to En star, but let's do things slightly more generally, and then you will know. Yeah. So what is G phi? So I want to know what is G phi. So if I know what is G phi on EIs, then I know what is G phi on the whole of V. Yeah. Because G phi is a linear map of V. So if I know what happens to the basis, then we are good. So G phi of EI we know is phi of G inverse EI, and G inverse dot EI, but is same as A inverse EI, yeah, because phi V of G is A, so phi V of G inverse is going to be A inverse, and then we have the usual action. Yeah, A is the matrix with respect to so A is the matrix of rho Vg with respect to E1 to En. So you get this A inverse Ei. Huh? So what is phi of A inverse Ei? So phi is this map. Phi is this linear map summation ui ei star I equals 1 to n. So since I have here ei, so I'll just replace this index by j. So maybe I'll do it here itself, yeah, so that there is less confusion. अरे क्या हो गया है? हाँ. Suddenly, no, sometimes this just goes mad. नहीं तो भी लिखने हैं. Okay. Yeah. So this phi is this thing, yeah. Okay. So now you think about it. So now you just replace phi by this formula. Then you get this is same as j equals 1 to n uj ej star a inverse ei. But what is a inverse ei? It's just you're picking out the ith row, yeah, of A inverse. That is how the matrix multiplication works, right? So if you take any matrix and multiply by EI, you are just picking out the ith row or ith column. What do you pick out?
Will it be the column over here?
It will be the column, huh? Yeah, it should be a column matrix, but yeah, so the first entry is going to be the I1th. You pick out the ith row, right? Yeah, you pick out the ith row. It's written in terms of in a column thing. Yeah. No, yeah, you are right. You pick out the ith column, right? So I've written this. I've written wrong, I guess. Yeah. Yeah. So ith column is what you pick out. Gi. Yeah. So this is all right. So you pick out the ith column, which means the first indices will change. Yeah. So you pick out the ith column, and then if you evaluate, so you pick out the ith column. So this is maybe this times e. So maybe I should write one more step here. Okay. So this is okay, ej star of I. So you are picking out the ith column, which means j I j. So maybe k I of the inverse matrix k equals 1 to n ek. Yeah, so you can write it this way, right? So but ej star ek is 0 most of the time unless k is equal to j. Yeah, so this becomes same as summation uj a inverse ka j ith entry. Okay. So this is what you get. So I hope I haven't confused you guys. Yeah. So this is what you will get. Okay. This is the formula you get now. G phi, of course, again you can write it in terms. So G phi is some element of the dual. Yeah. So you can again write it as some linear combination of EJ star dual, which is VJ. So VJs are basically the coordinates of G phi with respect to E1 to E star. Yeah. So G phi is, if G phi is this guy, then G phi evaluated at EI is just VI. Yeah. So what it means is that this guy. So what it means is that summation over J equals 1 to n uj. Yeah, maybe I should have just left this as a homework. Ji. This is same as Vi. Okay. So this you can check. Tells you that if you so this is if you do A inverse transpose and multi. So this is multiplying this matrix A inverse. Sorry, this is. This doesn't make sense. Yeah, I want a number here. Yeah. So so if so you can check that this precisely in terms of matrix notation. This set of equation for I between 1 and n precisely means this A inverse transpose U is V. Okay. So you just have to do the transpose. You have to do A inverse and then also do the transpose. So hence what you get is that the matrix of G with respect matrix of G acting on V star with respect to dual basis is the matrix of G with respect to the given basis, takes the inverse and then do the transpose. Okay. So this is the formula for the dual representation. Yeah. So if you want to compute in terms of matrices, this is what you get. Okay. Any questions? So I hope this is somewhat clear. So this to this step is also not bad. You just expand it. Yeah. This side, if you expand it, this matrix notation, you should get this thing. Okay. So this I mean this is basically, if you think of U as a row matrix followed by and multiply it with A inverse, then you get a column matrix of V, a row matrix of V. Yeah. So to write it in terms of column, you just do the transpose. So that is what is done. Yeah. So this is also, I think this step should also be clear to you. Okay, so that's where the transpose comes in. And then this leads to so, and we already discussed that this gives you can how to get a representation on VW. Yeah. So to verify that this is an action, you do the same set of steps to get that this is indeed an action. So there is, so I'll just assign one homework problem. So you see, so you did, okay, so this, I don't know if you have seen this in linear algebra. Maybe since tensor product you haven't seen, so you may not have seen. So maybe that part is also a homework. So maybe homework, yeah. So home VW, you can also think of it, so V and W are two vector spaces. then this is isomorphic to V dual tensor W. Okay. So first you have to give this isomorphism. Yeah. So homework is this isomorph. So first as vector space, and then as so if V and W are representation, so E, and then part B will be if V and W are G representation, then show that. So it is isomorphic in some natural way. Show that these are the two representations are isomorphic. Representations are isomorphic. Yeah. So if V and W are G representation, then we know that this left-hand side is a representation, which we just defined. We also know V dual is a representation, which we just defined. W is given to be a representation. So that tensor product is a representation. We defined that last time. So you have to show that there is a natural isomorphism which is G equivalent. Yeah. So this will be yours. So this will be a nice exercise to do. Okay. Okay, so now you know how to get many representations. Yeah, so one way is to so one way is characters. You can take direct sums of representations. You can do tensor products. You can take dual, yeah, and you can also do homes. So there are many ways of cooking up representations. Okay. Now let's so we will do this Schuh's lemma as well, but let's do character theory. So since I'm following Cher, so he does defines character before going on to Schuh's lemma. Yeah. So let's define character, which is an invariant of the representation, and maybe next time we will do Schuh's lemma. Okay. So is this visible? Maybe I can make it slightly bigger. Yeah, this is okay. Otherwise it will go out. Okay. So let G be a G representation. Then the character of rho, which is denoted by chi sub rho, is a function from G to C. Yeah. So I guess the base field C is not necessary, but maybe for some lemma, some proposition it is necessary. You can define character of any representation. K need not be any field. But anyway, in this course we are thinking only of C. Yeah? So the way to define it is you evaluate. So chi rho of G is just trace of rho G. Yeah. So it's some function. I mean, it doesn't have any. So it's need not be a group homomorphism or anything. Yeah. Or I mean, sometimes like if you start with a one-dimensional representation, then of course it is the character is same as, I mean, then what you get is the matrix is one by one matrix. So the trace is that matrix itself. Yeah. So then of course it's there is no difference between character and the representation. Yeah. So in one-dimensional case, you can it's obvious that not only character is not just an invariant, it's the whole thing. Yeah. So the representation is determined by the character itself. So this is true more generally. Yeah. So of course, if two representations are isomorphic, they should give it should give you the same character. But even the converse is true. So if you get the same character, the two representations are also isomorphic. Okay. So that we will see later. So, yeah, so maybe, so for one dimensional, this is just that's the homomorphism, but for higher dimensional, it's not. So first thing is that from character, you can read some things easily. For instance, the dimension of the representation, you can just read it up. Because if you evaluate the character, if chi is the character of this representation V, then representation V meaning, okay, maybe I should just put it G as well, G representation. So G representation V, then chi of the identity element, which sometimes is denoted by 1, sometimes by E, is same as the dimension of V. If you take the inverse, then if it's a complex representation, then it's what you get is the conjugate. Yeah, so it's some complex number, you just take its conjugate. Chi G is some complex number, you take its conjugate. That is what this guy is. And if you conjugate element of G and you calculate its and evaluate the character at that, is same as the value at H. So in other words, character is a class function. Is so on each conjugacy class, it's constant. Yeah. Okay. So these are called conjugacy classes. Yeah. So it's so in IE. So this means IE is a class function, which basically means that on conjugacy classes, it's constant. Okay. So so the proof is straightforward. So let's do the proof. So what is chi of 1? So it's just the trace of the identity, yeah, trace of a row V of 1, which is trace of identity. Since row V is a group homomorphism, identity matrix, identity in element of GV, which is GLV, so which is identity of V, which is the same as dimension. So you just have, so that means you get the identity matrix, yeah, and you take so you just add up the diagonal entries, which are all 1. So that gives you dimension of V. So from character, you can just read out the dimension easily. So it's a funny kind of function, but it's a very useful function. Yeah. How about G inverse? So yeah, so I hope I can do all this from memory. So I wasn't sure if I'll reach here. So chi G inverse. This is by definition trace of row G inverse. Yeah. 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 So how do you compute the trace of element of GLV or trace of a matrix? You can look at it as eigenvalues, yeah, and sum the eigenvalues. Yeah. So let lambda i's be eigenvalues of values of rho G. Yeah. So it's some matrix. So it will have lambda 1 to lambda n. So let's say which is n. The dimension is n. Yeah. So it will have n eigenvalues, possibly repeating. So lambda 1 to lambda n be eigenvalues of rho G. Yeah. Then chi G inverse is basically sum of these lambdas, lambda 1. So lambda 1 to lambda n. So some of these lambda is, no, not lambda is, but some of the, so chi, if the eigenvalues of rho g inverse. So what is the eigenvalues of rho g inverse? So if A has eigenvalues A1, some lambda 1 to lambda n, then A inverse will have eigenvalues what? Is it lambda 1 inverse to lambda n inverse?
Yes, sir.
Yes. So this is lambda 1 inverse to lambda n inverse, yeah. And remember, rho g is a matrix of finite order. I mean, the order of the meaning the as a element of the group GLV is of finite order. Yeah, it has so because G power n has to go to is G power the size of the group has to be identity. Yeah, so that tells you that the minimal polynomial is going. So the eigenvalues are all roots of unity. Yeah, so some power of the matrix is identity. Yeah. So the minimal polynomial divides x power n minus x power m minus 1 for some m. Yeah, for instance, so you can take m to be the size of the group, for instance. Yeah. So all the eigenvalues of are roots of unity. So these are at least on the complex so unit circle, but anyway, we know it's actually roots of unity. So lambda i's are roots of unity. So lambda I inverse is just the conjugate. Yeah, so this is same as summation lambda I bar equals 1 to n. Yeah, but summation lambda I bar is yeah, so this is same as chi g chi g bar. Yeah, that is what we want to. So you can just take bar at the after adding. Yeah. So that tells you number 2, and for number 3. So what is the number 3 says? Yeah, yeah. So that is also straightforward, I suppose. Yeah. So this is trace of we want to show trace of rho g inverse hg is same as trace of h. Yeah, so we will do this. So this left hand side is trace of rho g inverse some matrix rho h, since rho is a group homomorphism, times rho g. Yeah, but we know that trace of AB is same as trace of BA. Yeah, so that you must have seen from being algebra. So you think of this matrix as A and this as B, and then this is same as trace of rho h rho g times rho g inverse. Since trace AB equals trace BA. Yeah, so this by using just directly the formula. Yeah, so this actually is true for any matrices where you can multiply any two. So even if A and B are not square, but their product is a square matrix, then also this formula is true. This is more general. Yeah. And this, of course, is same as trace of rho h. Yeah, so maybe I can just equate these two. Yeah. Sorry, I should put a rho here. Rho h. Okay. So that completes the proof of these basic properties of of characters. Okay. Any questions? Okay, so yeah, so the next thing is the Schur's lemma. So maybe it's not a good idea to start it now. Yeah, I mean, even if I start, I'll just state the result. Yeah, so and then I'll have to reproduce it. So I'll just tell you what the result is. So Schur's lemma, maybe I told you already. So Schur's lemma tells you, so if you have two representations, V and W, and suppose that they are irreducible representation, and suppose you of the same group G, and suppose if you have a equivariant D equivariant map between V and W, then there are only so there are not too many of them. Yeah, so so if V and W are so if this equivariant map is so one option is that you take the zero map. So it is either zero. So if V and W are not isomorphic, it's going to be zero. And if it is isomorphic, then it could be a scalar it is basically a scalar multiple. Yeah. So so the map is V. Yeah. So it's not any. Yeah. So the map is V goes. Yeah. So scalar multiple means. Yeah. So it's just some. Yeah, so then of course, if they are isomorphic, then you can you have to fix an isomorphism between V and W. So you identify W with V, and then after that identification is just scalar multiplication. Yeah, V going to G, some A times V, where A is some elements of the base tree. So that is what Schur's lemma says. So there are not too many G equivariant maps between irreducible guys. Yeah, if they're different, there's only zero. Otherwise it's a scalar multiple. So that's the content. So the proof is also not difficult, but anyway, yeah. So proof is also maybe 2-3 lines, but it will anyway shoot over, which I don't want to do today. You have a class immediately after. Yeah. So we'll talk about Schur's lemma next time. And maybe we'll do some more examples as well. So we haven't seen higher dimensional representation. So maybe next time I'll also give you some higher dimensional representation. We'll calculate some characters as well. And so I didn't think about. So if I had done some examples, we wouldn't even have time to talk about Schur's. So yeah, so next time maybe I'll give you some higher dimensional representation. So I mean, of course, we can take regular representations and stuff and calculate this character as well. So maybe we will do something along that line. Okay, maybe it's a good place to stop.